Welcome to lecture number 4 for Computer Science 4303. If you're wondering why I'm wearing this hat, it's not because I'm a homeless fisherman, but because we're currently in the middle of a blizzard here in St. John's, and I just had to go get some gas for my snowblower. So the hat completely messed up my hair. It looks like I just woke up, so I just decided to keep the hat on. All right. So today we are going over movement in games, which is probably overall the most important part of AI is, you have a character in a video game, you want to go from one point to another. That is really, really important. So we'll be talking about that. Last class, I talked about Assignment 1. So Assignment 1 has been officially released, and you're working on that. That'll be due on the 2nd of February. And I hope everyone is going to have fun with that assignment because I had fun creating it. And everyone should have their links for that assignment. So there's no excuse not to have it done on time. And remember, if you are looking for a partner for the assignment, you can click on this link to go to the spreadsheet for finding a partner. So you don't have to do the assignments alone. They can be done in groups of up to 2 people. Okie doke. So let's get started with the lecture. Here we go. Oh, the Stream Deck works. That's awesome. I bought a Stream Deck, and I don't have to look over at OBS and scroll through my list of scenes. I can just click back and forth. Like, for example, oh look, it's my full screen camera. Oh look, it's my PowerPoint. That's really nice. Less mental load while you're teaching is really good. So, movement in video games we'll be talking about today, as well as steering behaviors. So if you took Computer Science 4300, you're already familiar with steering behaviors, but they don't take too long to talk about. So let's go over both. So movement is arguably the most important part of a large number of video games, right? So you're controlling some character and you want it to move somehow to some destination, either to an enemy or to a goal or to pick up some food. That is a very important part of a video game, and that is all controlled by the AI system of a video game. Or at least AI programmers think that movement falls under their jurisdiction, right? It's a set of algorithms or many different types of algorithms that can do movement in games is typically thought of as an AI or artificial intelligence behavior. So movement allows the exploration of the game world and interaction with entities. And not only does a player move in the game, but the NPCs and other entities in the game do as well, right? So if you you might just have one player, but maybe we have 100 entities that are walking around, or 100 NPCs that are all trying to get somewhere. So coming up with really efficient representations of the space in our game and algorithms to move ourselves around in that game is very, very important of game programming. And good movement makes a good game, right? Like, who's played a game where the movement felt clunky or the controls felt clunky and the movement was annoying and that just completely ruined the game for you? I know that I have. So there are several main problems in video game movement that we're going to try and solve. So one is called path finding. So path finding is the problem of finding a path from point A to point B, right? So I've got an NPC who wants to move from point A to point B. The first problem that I have to solve is to find the path that can safely move me or most efficiently move me from point A to point B. After I've found a path, then I have to follow the path. So this is called path following. And so how we move the character along that path is just as important as the path itself, right? And I'll show some examples, funny examples from video games where maybe the path wasn't followed so correctly or the path wasn't computed correctly, and how that affects gameplay and affects the user's overall opinion of the game and maybe how many sales it gets and stuff like that. There are physics involved in movement. So for example, how the environment reacts to your movement. Maybe you can go up a hill and you start sliding down or something like that. There's also animation is an important part of movement in games, right? So if you're running along at full speed and you tell your character to go in the opposite direction, Well, some sort of animation should show that, right? Like in really old video games, maybe you just turn on a dime and go in the other direction. But ideally, in a more realistic looking video game, there's some sequence of animations that has to play, like you're running, then you're slowing down, then you're turning, and then you're running in the opposite direction. So animation is also a problem that falls under AI in games. Now, that's not how to animate, like actually defining the frames of the animation. That's up to the animators and the 3D modelers and stuff like that. But when the animations get played during movement is part of the AI system. But in this course, we'll really only be looking at those first two problems, okay? Physics is a really complicated problem that we're not getting into in this course, and so is animation. So we're not going to be getting into physics and animation, but we will certainly be spending some time on both the path finding problem and the path following problem. And Computer Science 3200, the Intro to AI course at Memorial, where this course is being taken, it went over some pathfinding algorithms as well. So we went over breadth first search and depth first search and their variants, as well as the A-star search. And so we already know, if you took the prerequisites for the course, some people I know didn't, how to do some pathfinding. And so it doesn't make sense to take a bunch of time relearning A-star in this course if you learned it in a prerequisite course. But of course, we will be looking at that a little bit. But in this course, I want to go over some different algorithms that we didn't cover in that course. So in this course, we'll be dealing with AI decision-making for movement. So path finding and path following, those decision-making problems, but not the physics or the animation. So I just wanted to show some really quick clips. Some of these I showed in Computer Science 4300, and some of them I didn't. So here's an example from the Saints Row series of games. And this is what I call like 3D pathfinding, if you will. Where can I put this safely? Up here, I think is fine. All right. So this is an example of pathfinding. If it will play. No, it's not playing. 1 second. There we go. So here is an example where you have this 3D world, and there was a pathfinding algorithm that ran that said, hey, there's a safe path over this bridge. But then when the bridge went up, you can see the effects of this, right? So not quite such good pathfinding. It wasn't dynamically changing while the bridge went up. So let me just show that again. You know, pretty funny effects from what can happen if you compute a path once and then continue to try and follow it, even though the environment has changed since you last computed your path. Here's another funny example from Skyrim. So Skyrim, of course, is known for its AI bugs, and pathfinding is no real exception to that rule. So here I've labeled this as threat-aware pathfinding. So in Skyrim, littered throughout the game, and especially in the dungeons, are a bunch of different traps. And so these traps can be triggered by stepping on like a pressure plate or something like that. And what you'll see in this clip is a pretty funny example where an AI in the background, I don't have the sound turned on, but it says, ooh, what was that? And it comes to try to investigate, and then you'll see what happens after the investigation. So here comes the NPC. You can see it trying to find the player, but the player is sneaking. It steps on the pressure plate, and boom, there's the trap. And this enemy just saw that happen, but of course it's a Bethesda game, so enemies will just trickle in and keep dying and dying to stuff like that, right? So ideally, we would, in a perfect game, we would want to have some sort of threat-aware pathfinding that said, okay, you know, if this NPC lives in this dungeon, it should probably know about that trap, and so maybe it shouldn't step on it. Just maybe. We also have problems where we could have multi-agent pathfinding. So those two examples were just single-agent pathfinding, where you're trying to take one agent from a start to a goal. But we could also have a bunch of different agents. So I've put in two different problems here. One I'm calling move as group, and the other one surround enemy. So these are examples from StarCraft Brood War, and if you've played StarCraft Brood War, some of the pathfinding was notoriously not great. So in this move as group example, what we have is a group of 10 or so siege tanks, and the siege tanks want to move from one side of a wall to the other side of a wall. And if you've ever played an RTS game, or really any video game, you know that if you have a group of units, you want those units to move as a group, right? You don't want them to sort of trickle in single file. Sorry, I've got a hair in my eye. You don't want them to trickle in single file, because if they do, then they're going to be picked off one by one. It's much more powerful if that whole group of units moves as one. But it turns out what the StarCraft Brood War pathfinding engine does under the hood, well, first there are collisions between units. And so if two units are trying to occupy the same space, they'll just kind of butt heads until one of them takes the space, right? And so what's going to happen is that you're going to see these units trying to move as a group, but they can't move as a group because the underlying pathfinding engine creates a single path for all the units and then tries to get all those units to follow the single path. So let's see what that looks like. Here I've selected all the tanks, and I tell them to move to a specific location, and you can see that what's going to happen is they're going to move single file to that other location, right? And so what's going to happen over here, it's pretty bad. You're just going to see these units get picked off one by one by the enemies, and you don't want that to happen, right? Okay, so next, I have that example, if I can somehow go back. This is kind of surrounding the enemy. So an important part of any RTS game is to be able to surround your enemy with your units. So what I've done here is issue the attack command for a bunch of workers to attack this larger command center. And you can see that all the units are getting stuck on each other. It's taking a super long time, excuse me, to surround the building. And this could have been done a lot more efficiently, right? So let me just rewind that once more and just show you how long it takes to actually surround that building. Right, so if you were making some pathfinding system that sort of knew that you wanted to surround something, you would send the units maybe beyond that command center and then come in from all sides or something like that. So there's all sorts of different goals that we could have with pathfinding. But not all pathfinding is bad. StarCraft 2 greatly improved the pathfinding system from StarCraft 1. And you can see here a group of over 100 Zerglings pathfinding all together. And these are actually like moving as a group, moving as a swarm. And you can just see like, oh, like, wow, how much better this pathfinding is than in the last version of the game. Now, there are some little tricks that they're using here. Like, for example, when they select a group of units and move them as one, they can sort of group on top of each other and then rubber band outwards. Let me play that once more. So you can see that when they tell them to go to one spot, the units sort of overlap at that spot, and then they gradually spread out again. So that's just a little bit of cheating that happens in order to make that pathfinding possible. But it's a way better example than, or it was a way better pathfinding system than was available in StarCraft 1. Okay. Also, we are concerned with realistic behavior. So here we have from Dragon Age, a group of NPCs that enter this house, and you can see, like, the pathfinding, some of those units in the background end up getting stuck, and this behavior just is completely taking away from any drama or meaning in this scene, right? So this is not a great example of pathfinding in that game. But the pathfinding in Dragon Age was actually pretty good if you played the game. It's just there are a couple of these scenarios where I think the goals for these units may have been in spots that were like on the other side of the wall. So that's pretty distracting. Also, we would want to have sort of realistic paths. So if you can see this NPC here about to run to us, what the user did, let me actually explain this before I play it again. So the user was on this little slope, right? On this little metal slope. And the NPC was running toward the user. But when the user took like 3 steps to the right, the NPC then recalculated its path, but it was like the worst possible path. It ends up going around the entire level to get back to them. So just watch. You can see the NPC coming toward the user. Then the user goes, or the player goes to the right a little bit. And now watch the path that this NPC takes. It'll take a minute, but it's worth it. And this is from Fallout New Vegas, so, you know, another great game, but also known for its quirks. Here we go. All right, so try not to find that path. So, you know, the NPC was in a hurry to get to the user to give them this thing, but, you know, the path it computed wasn't that great. And also, animation matters in your paths, right? Just, this animation is pretty funny, but no matter how smart your path is or how refined your pathfinding is, if you've got a horse stuck on 2 legs in midair, that's going to take away from pretty much everything, right? So yes, animation does matter, but we're not going to be going over animation in this particular course. So just make sure that you have decent animation system when you actually execute your pathfinding. So, pathfinding. Formally, what do we want to do when we're talking about pathfinding? So, video game maps, they're often filled with obstacles, and the obstacles might be walls or other NPCs or landmines or whatever, with which the NPC will collide, and some various effects might happen from that collision, right? So if you've got spikes on the ground, maybe the user would die and you don't want that to happen. Excuse me. If it's just another NPC, maybe that NPC will start attacking you like Grand Theft Auto. If it's just a wall, then your path is going to be either really a lot longer to get to your destination, or maybe you won't even get to the destination. And so you're trying to avoid obstacles in some way. So pathfinding is the method we use, or the algorithm that we use, to determine which path an NPC should take from its current location to some goal location. And pathfinding attempts to minimize a cost of the path. So we're going to assign some cost function to a path, and that cost function could be, maybe it's the total distance traveled by the path, right? So if I've got a path like that one we saw from Fallout, that first path was going straight to the user. So that would have a really low cost if our cost was path length, versus the second path was super, super long. And so ideally, we would want the shorter path in that scenario. So we're going to define some sort of cost that could be path length, but maybe it could be, for example, fuel consumption, right? So maybe you'd be willing to drive somewhere in your car and have that take a little bit longer if you saved fuel or money, for example. Maybe you could also be playing like a tower defense game or something like that, and you would want to have a path that's not necessarily the shortest path, but the path that had the least amount of damage taken, for example. Or any arbitrary function. Maybe it's the most points in the game or something like that. So any arbitrary function, but we have to have some numerical function that we're attempting to minimize, and that is up to us as the programmer. Well, you would talk to the game designer and say, what is it you want the NPC to do in this scenario, right? And the designer would say, oh, the NPC wants to get to you, but maybe it wants to be really stealthy, so it wants to avoid being seen. Or maybe it just wants to get to you as fast as possible. So you would take that design decision and you would turn it into a numerical value. And that numerical value is going to be the cost function that your pathfinding algorithm is going to minimize. So if you think back to something like the A-star algorithm, where we have F, which is our evaluation, and then we have F is equal to G plus H. So the cost is going to be the G value, and the heuristic evaluation of the cost is going to be the H value, okay? So you sum up the cost so far, that's your G value, and you have some heuristic value which guesses how much cost I have left to go. We also need to make several considerations when we do pathfinding. So for example, those considerations could be, well, is this a single agent pathfinding problem or is it a multi-agent pathfinding problem, right? And our choice of algorithm, our choice of method, our choice of data structures is going to depend on all of these considerations. For example, another one is there a single goal or maybe there's multiple goals, right? And so an example of a single goal is I want to get this NPC from their current location to the player's location. That's a single goal problem. But maybe if you're in like a firefight with the NPC or with the player, and you want to get the path that's to the closest med kit, right? So, or the closest fuel station or something like that. So there could be multiple goals, but you're trying to find either one or more of those goals. So that also affects which algorithm that we choose. Also, there's the choice of static or pre-computed paths versus dynamic or online or constantly changing paths, right? So what do I mean by a static path? Well, what we could do is, for example, I believe in StarCraft Brood War, some of the paths are statically computed. So what that means is that, maybe not in Brood War, but in some games definitely, there's going to be like waypoints and in the level, and the paths between those waypoints are going to be pre-computed, right? So maybe if your game environment doesn't change that often, you can pre-compute all those paths, and then you can store them in some data structure when you release your game. So when you're pre-computing paths, you don't need to have them run as fast as if you're computing them online. But if we have dynamic paths where, let's say, for example, in Fallout or in StarCraft, where you have units moving all over the place, ideally you would want to have paths being recomputed all the time so that they don't get stuck on other things which are potentially moving around, right? Because if we statically compute a bunch of paths and then something is blocking that path when we actually go to run the game, then it won't be recomputed and things can get stuck. But so dynamic paths are preferred for sure, but they're much more expensive because things are moving around and dynamic things are always more expensive to compute. And they're more expensive, but they have to run faster because they have to run while the game is running. So you may only have a few milliseconds to compute a dynamic path. Also, your space representation is going to matter a lot. And so we're going to get into all of these different space representations. In fact, in the next lecture, we're going to talk about the grid representation and how a lot of games use grids. But in a future lecture, a little bit later in the course, we're going to be talking about graph representations, nav meshes, polygons, all sorts of stuff. And your choice of how you represent your states and your actions is obviously going to have an effect on which algorithm you can use. Also, you have to choose, okay, what movement directions am I going to allow? So for example, in a really simple game like Legend of Zelda for the NES, maybe you're only allowing up, down, left, and right, so sort of compass direction movement. Maybe in a more modern game, you would have arbitrary angle movement, right? So you can move in any direction. I can click anywhere on the map and my character should move there. So it's like something like League of Legends, right? Or Dota, where you're playing a MOBA game, you have a character, you can right click anywhere on the map and it should be able to run at any angle to get to that point. Or maybe you have like movement between nodes on a graph, right? So maybe your game is sort of like Civilization, where you have this hexagonal structure where you can't move arbitrarily, you can only move between these specific nodes on a graph. And so maybe that problem is a little bit easier than arbitrary angles or movement. And so when you're making your game, you've got to sit down with the designers of the game and say, okay, what do you want the movement to look like? What sorts of pathfinding do you want? Like, is it multi-agent, single agent? Is there multiple goals? Do you want paths being updated in real time, etc., etc.? So you will ideally, after talking about that with the designers, or maybe they're just going to give you the design of the game, then you've got to take those constraints and construct the system for computing pathfinding that meets those constraints. Okay, so let's just look over an example of what might happen in a case of pathfinding. Okay, so let me move this over here. So here we have an example of, and with pathfinding, usually we have some environment. So here we have like maybe some blue water. We're moving around in the water. We have some green land here, and we can only pathfind like within the same color, for example. So anyone who did 3200 should be kind of familiar with this structure. So here we have an example of single agent, single goal problem. Okay, So we have one agent over here. So this is a starting location for one agent. And down here we have one goal location. So this is really the easiest form of pathfinding. You've got one thing that you want to get to one place. That is probably the simplest form of pathfinding. Next, we would have something like, okay, multiple agents with a single goal. And anyone out there in the chat can tell me an example of a game where you would want to have a pathfinding system that is capable of computing multiple agent paths to a single goal. I'll wait until someone responds. Let's get some class participation here. Any ideas of a game where you'd want to have multiple things heading for the same thing? Nobody? I thought we had a bunch of gamers in the chat. Come on. Rocket League? No. Tower Defense? MOBA minions? Yes, there's a great example, okay? So in a MOBA game, you might have a bunch of minions that have been told to move from your base all the way down a lane to the other enemy's base, okay? I think probably the most canonical example of this would be a game like Diablo, like an action RPG, where you're controlling one character and basically every character on the screen wants to kill your character, right? So if you play like Path of Exile or Diablo, you might have 200 enemies on the screen or a bunch of homing missiles or whatever that are all trying to get to you, the player. And so that's an instance where, hey, we probably don't want to have to compute 200 separate paths to a single goal. And so what can we do? Well, actually, assignment 2 is going to be on that very topic. So we'll talk about that in a lecture or two. We could also have single agent, multiple goal, right? So for example, maybe in a level that you have to get to one of many possible goal locations. Or maybe there's an item that you want to pick up, like a health pack or an ammo pack, and you're just trying to get to the closest one, right? So all of these different type of pathfinding systems have different design decisions that need to be made and different algorithms that can carry them out. Excuse me. All right. So we talked about space and action representation. What do we really mean by that? So space and action representations are very important decisions, and the ideas are linked. And so which representation to choose is, again, it's a game design decision, but it's also your decision. Because the game designer is going to tell you, I want units to move in this sort of way, right, in order to fit with the theme of the game. But you, as the AI programmer, probably have a lot of freedom in how you choose the space representation for your game or the action representation for your game. And so the choice of space representation in your pathfinding engine will determine which movement actions can be performed. It will determine how you represent the start, how you represent the goal, how you represent a path, however. Okay, so let's look at an example, some examples of these. Let me make the camera a little bit smaller up here. So some examples of space representations. So in the most general possible case, you've just got arbitrary movement. So for example, over here, I've got a starting location. Over here, I've got a goal location. And in this arbitrary movement example, what I mean by arbitrary movement is that the entity can go anywhere, it can turn in any direction, and all of its points are like real valued points, right? So for example, here we could walk on a nice smooth curve, or we could go however we wanted through this level. As we can, so that is the most general possible case where you could go anywhere and turn in any radius, etc. If we want to abstract that a little bit, we could have something like straight line movement. So here we have an example where we have a start and a goal, but we can only move in straight lines. Okay, so maybe we have a path that kind of goes down here and avoids the corner of this island, and then goes in a straight line to that point, and then goes in a straight line to the goal, right? So straight line movement, but again, maybe you can move in any angle. Here, again, if we keep restricting ourselves, maybe we have just 4-directional movement. So we're going to talk a lot about grids next time and grid algorithms and stuff. So I won't get into that right now, but very simple games might just have 4-directional movement. And so, for example, here, to get from this start to this goal location, maybe we move down until we get to here, and then we move right. Similarly, with 4 directions, maybe we could have 8-directional movement if our game still had a grid, but we wanted to give a little bit more freedom in the movement. Also, we could have something like a graph node movement. So rather than have like a fixed grid structure where we have like, so a grid is a graph in a way. A grid is a special case of a graph where we have a node sort of at the middle of each of these grid locations. But we could have an arbitrary graph structure where we no longer have, say, fixed distances between points on the graph, but instead we can put graph nodes wherever we want. And so what we would do if we wanted to do something like this is we could just choose a bunch of points which kind of represent the space in a nice way, and then we could run our algorithm on nodes in this graph. So we could move in straight lines here between any 2 nodes on this graph. And then if we have these particular nodes, then a path from our start to our goal might look something like this, which might be or might not be the maybe a slightly shorter path might be from moving from here to here and then here to here, right? So we would run the algorithm on the graph. What you will see a lot of the time, especially in modern game engines, is you're going to have a polygonal-based movement system. So instead of just having points like in a graph-based system, so you'll have nodes which represent points, what you're going to have is you're going to chop up the area somehow into convex polygons. Convex meaning that so one second. So this polygon right here is not convex, right? Because we've got this sort of chunk taken out of it. This would be a convex polygon. And in a convex polygon, any 2 vertices can see each other. Okay, so that's an important part of a convex polygon. Let me just restart this slide real quick. So in a convex polygon system, we chop up our space into polygons, and then we define which polygons can move to each other, right? So here I've got these little yellow bridges, and that's just an annotation which says this sort of like an entity that's in this polygon currently can either move to this polygon via this path or this polygon via this path. And the polygons don't have to be separated like I have here. I just wanted to show that, you know, these are separate polygons. And then what you can do, now what you have to do on top of that is say, okay, well, how can I move within this system? Well, the reason we would use convex polygons, and remember, the definition of a convex polygon is that any vertex can see any other vertex. And what that also means is that any point within the polygon can see any other point within the polygon. And so that means that if I am inside any particular convex polygon, then I know that I can safely walk without any obstacles from that point in the polygon to any other point in the polygon. So if I sort of define these points at which I can traverse from one polygon to another polygon, let's say my character is right here, for example, and I want to get over here in this polygon, then I know that it's safe to travel from here to the meeting point of these 2 polygons, then from here to the meeting point of these 2 polygons, and then from here to here. And so that's just another way to represent your space. And then if you think about it, how would you do the pathfinding here? Well, if you think about each polygon as a node on a graph, then what you could do is do a higher level pathfinding pass where you find the sequence of polygons that you want to move through. And then when you're trying to get from one polygon to another, then you would do that level of the pathfinding. So this is more of how, so the StarCraft 2 pathfinding engine works more similar to this way than the Brood War pathfinding engine, which worked on a grid-based system. Okay, so someone said my mouse cursor is not visible. Yeah, so I have this laser pointer here when I want that to be visible, but when I'm drawing, unfortunately, when you're using the pen in PowerPoint, the cursor is not visible while you're drawing. So let me just give an example of that. So if I'm drawing down here, unfortunately the cursor is not visible, but that's just a representation. That's a limitation of the software. So I apologize for that. Okay. So choosing a state representation is important. It matters, right? So first of all, the memory size is going to be dependent on the representation. It defines which actions are possible. It defines which algorithms are possible. And so what we're really trying to do is we're trying to choose a state representation which is a good balance between the computation and memory required to find a path versus the accuracy or realism of the final path. Okay? And so in certain games, certain representations make sense, and in other games, other representations make sense. Like, for example, in Zelda Breath of the Wild, we probably wouldn't use a grid-based system, right? Because the world is so huge, we would have to store values for everything in this grid, and it's just way too big, right? Maybe we'd want like a graph-based structure or a navigation mesh or something like that for a game that big. And typically in games, we would prefer to use a sparse state representation for easier computation, and then like later refine the path to look more realistic. So what I mean by that is if you have a really, really fine grid, then that is going to take up a huge amount of memory. So what you could have is like this graph representation. Maybe it produces paths that are really similar to the grid, but you have to store far fewer nodes in this graph representation than you do in this representation. So it definitely affects the amount of memory for your pathfinding system. Okay, some quick notes about navigation meshes and what they are, because I mentioned them already. But we will get into more detail about navigation meshes and about how they're computed in the future. So what if my game has completely arbitrary geometry? Then we need some sort of graph structure within our environment to enable pathfinding. And that graph typically is called a mesh or a navigation mesh in the game AI dictionary. And most game engines are going to come with software to build and edit a levels navigation mesh. So if you download Unity or if you download Unreal Engine, you're going to have some way to edit the navigation mesh for your level. And I'll show some example screenshots of that. And later in the course, I'll go into some of the more complicated, or I guess not complicated, but more complex ways of constructing a navigation mesh. And in assignment 2, we are going to be constructing a grid-based navigation mesh. Okay, so we will actually, it's going to be cool. You're gonna have an environment. You're going to have obstacles in that environment. You're going to have a grid structure, and you're going to construct a navigation mesh and then do pathfinding into that navigation mesh, and then add some NPCs who are walking around with the path that you construct. So we're going to be doing all this from scratch, okay? Some people wanted me to teach this course in, like, use Unity and just show them how to make a nav mesh. That's not cool. We want to do this stuff from scratch. Then when we go to use Unity, we're already gods, right? We know how it works under the hood. So here's an example from, a professional piece of software where you have a level. This is Unity, I believe. And you put some obstacles in that level. So for example, here you have the player in pink, and you're going to have some obstacles here that you can't move through, like these towers. And so what you do is the game overlays a default navigation mesh, which says you can walk anywhere. And then in this example, they're using a deletion brush to take out parts of the level that they don't want the user to be able to walk through. So here you can see this sort of blue graph structure, or this blue grid. That is defining the parts of the level that are walkable by the user, okay? And then over here, right at the very end, very quickly, you can see the user walking around on that navigation mesh. So we'll just wait for that to play, and then that's how that works, okay? So inside Unity, it has tools that allow you to build a navigation mesh, and it also has default pathfinding that is built into that navigation mesh that lets you walk wherever you want on the nav mesh kind of efficiently. But of course, this is an AI course, so we're going to be doing this on our own in this course. And as you get more complex level designs, especially when you get into 3D levels, which we won't be doing in this course, you will have like pretty complex structures. So for example, I think, is this, one second, is this a video? No, it's not a video. The video is the next slide. So give me 1 second. So in this case, we have like navigation mesh here on the bottom. I believe this was part of a video where they had like a spider and the spider could walk on walls and stuff. And so here you've painted navigation mesh on the floor, you've painted it on the walls, and you've painted it up here. And so the spider could walk from here to here, then go around. And so anywhere within that navigation mesh where it was connected, you could walk within the game. Here's another example where you might have things like, how do I explain this? So you might have different heights, and you want to be able to define, for example, okay, the user can go from this point in the graph, which is disconnected. So here, for example, we have a bunch of different steps that are slightly disconnected in the navigation mesh. We also have the tops of these pillars, which we want the user to be able to walk on. But maybe in this game, there's no jump button, for example. Right? And so rather than the user being able to jump on it, we may have something where we say, okay, parts of this navigation mesh are connected. Even though they're not directly connected on the mesh, what we can do is say, if you move in this direction from right here, you'll go to this spot. So the person making this nav mesh has put little spots of nav mesh on top of these pillars. And then they've built nodes here that say, well, if you walk up to the top of the stairs, you're going to be jumped over to this part of the nav mesh on top of this pillar, right? And between these pillars, you can jump between them. And you can see how this kind of gets a little bit annoying, right? There's a lot of content authoring that goes into something like this. But if you want your game to behave as expected, then this is just something that you're going to probably have to do, is when you construct your navigation mesh, be very, very detailed like this. Okay, just 1 second. I have a surprise for everybody. Look who just came into the room. This is Luna. Say hello. So, Luna wanted to sleep under my couch behind me, so that's why she came in. People have been asking me to show my pets more often, so whenever I get a chance and they're around, I'm definitely going to show them off. Let me just let her out. I think she wants to leave now. All right, so there was some kitty. I had a question in the chat, but could you also automate generation of those meshes in a pre-compute phase, right? Like in the case of those pillars, auto-generate meshes between any pillar. Yes, that is completely correct, and that's a great point. So this is called baking the navigation mesh. That's one of the terms that they use, where you sort of define rules for the nav mesh and you set up an algorithm and it will bake, you know, the algorithm will compute the nav mesh and bake it into your level and do all that sort of thing. So this does not have to be manual, but there does need to be some sort of rule, right? Like you wouldn't want it to be able to jump from over here on the stairs all the way over, let's see if I'm allowed to draw on a video. You wouldn't want that to be possible, right? So you would have to define some sort of set of rules, and then maybe you could have an algorithm generate the nav mesh for you. So that's a really good point. And it's not always as manually intensive labor as it seems. Okie doke. So what is the pathfinding workflow? So we've talked a bit about this so far. So first, we need to identify the problem that we're solving, right? We need to know whether or not we're trying to minimize the distance, we're trying to make a more realistic path, we're trying to save fuel, we're trying to minimize damage. We have to identify the problem that we're trying to solve and the cost function associated with that problem. Next, we have to construct a space representation. So whether that's a grid, a graph, a navigation mesh, we have to have some sort of space representation. We have to decide which actions are possible within that space representation. Then we have to either come up with or be given a start and goal location, right? So my character is currently at this location. I want to get to another location. And whether or not that is single agent, multi-goal, whatever, we have to decide on all of that. Then we have to think up or choose an algorithm which finds the path, right? And that's completely dependent on all of these things so far. So each of these four things, the problem, the cost, the space representation, the actions, and the start and goal location, that all determines like which algorithm we can apply to this. And so then once we have applied the algorithm that finds a path, now we have to follow the path from the start to the goal. So let's look at an example of this in visual form. So let's say this is our space, okay? We've got some platforms here, and we want to do some path finding. So first, we've identified the problem. So let's just say, for example, we're going to have a single agent and a single goal, and we're going to want to minimize the distance, right? That's a pretty standard pathfinding problem. So we've identified the problem that we want to solve. Single agent, single goal, minimize distance. Next, we're going to want to choose a space representation, right? So in this case, maybe I've broken up the space into different polygons. And so here I have polygons like C1, C2, C3, C4, C5, C6. Maybe they're triangles, maybe they're arbitrary polygons. I think here they're quads and triangles, but we've broken up the space into some sort of representation. Then I have to be given a start and a goal location. So up here, for example, right, you can see this is where I'm starting, and this is my goal location down here. So my player's up here, they're down there. So I've identified a start location and a goal location. Now I need to choose an algorithm that can deal with this, right? So let's say I've got, I don't know, nodes on this graph, on this nav mesh, and I'm going to apply the A-star search algorithm. So I come up with some path, and then maybe I refine that path a little bit. So how I actually follow the path matters, right? So this is my path at a high level through these polygons, but here is the actual path that I may want to follow, right? I go from here to like the corners of this polygon, and then I follow it through, and then I actually walk along that path and I reach the goal. So that's the overview of the entire movement system. Okay. Path following is different from path finding, right? So finding the path is one thing, following the path is another thing. I just had a question in the chat about the course schedule and contents. Yes, so I teach now at this time slot every Tuesday and Thursday at the same time. And that's going on until April, and you can type playlist or course to get the lectures, but the course assignments and slides are not available. Okay, so path following. Now that we have the path, how do we actually make our agent traverse it in the game? That's a completely different problem. So the simplest way to do this is via waypoints. So each point along the path is a waypoint. The path to the next waypoint is always clear. That means that whenever we choose waypoints, we want to choose waypoints such that we absolutely know for certain that going from one waypoint to the next waypoint is a straight line and there are no obstacles. Because if there were obstacles, then we'd have to do pathfinding between the waypoints, and that's not what we want to do at all, right? We want to do one sequence of pathfinding. And then we're going to walk from one waypoint to the next waypoint, and then we're going to stop when the NPC reaches the goal, when we're out of waypoints, when we've reached the last waypoint. So what might that look like? Okay, so here's what that could look like. So let's say that we have a problem where we have single agent, single goal, 4-directional movement on a grid, right? That's like the simplest possible case for pathfinding. And if you did 3200, you're very familiar with this. So you want to go from this start to this goal. So you've created the path, which is the sequence of actions. But if you actually want to follow that path in the game, let's say, okay, you've got a grid representation here, but maybe my NPC or my player in the game can actually stand at like arbitrary positions in this grid. So what you want to do is you want to have a series of waypoints so that you have to go from one waypoint to the next waypoint to the next waypoint to the next to the next to the next to the next. Oh my God, okay, there's a lot of waypoints until you reach the last waypoint, which is at the goal. Okay, so that's how you're going to implement this path following and how it's implemented in most games. But as we can see, this is a little bit of overkill, right? Like, do we really need all these waypoints? Well, what we could do is say, okay, let's skip half the waypoints, for example. So every second waypoint I've skipped here. So now we're going from the start here, we're going to the first waypoint, then the second waypoint, then the third, fourth, fifth, sixth, until we reach the goal. And we've accomplished the same thing. However, is this the fastest path in this game? Well, our path finding system, it used 4 directions, but our path following system may have an arbitrary directional movement, right? So for example, what I could do is something like this, where I say, okay, I'm going to move from the start to this waypoint because I can see this waypoint, and then I'll move from that waypoint to the goal. And now we have a much faster path than this one, right? So the path refining stage involves eliminating some of those waypoints from the path in order to make our movement either faster or more efficient or more realistic or whatever. And then when we've found the final, when we've refined the path to the point where we have the minimum amount of waypoints, right? Then what we can do is refine that path using some method to maybe make that a little bit smoother, right? Because we don't want our NPCs walking around and turning on a dime and then walking and then turning and then walking and turning and that'll look really robotic, right? So how would we implement something like this? Well, it was in the title of the lecture, right? And that is a steering behavior. And so what a steering behavior is it's literally just what it sounds like steering a car, right? If you're in a car and you want to make a turn, it's going to be a slow and gradual turn about some radius, right? You can't just turn on a dime in a car, despite what the manufacturer might tell you. It does have a nice smooth turn. So a steering behavior is something that we're going to implement in order for our movement to look more realistic. Okay. So steering behaviors. So steering can be seen as a framework for controlling autonomous agents such as robots, CGI, NPCs, etc. Steering adds more realism and fluidity to agent movement, and it can really help enhance the experience in a game. And steering can be really fun to implement. You can play around with, there's a bunch of different parameters, and you can see sort of what effects can be produced, etc. And so at its core, steering smooths the movements of entities in games. Well, that's what we're going to be using it for. Changing directions instantaneously in your game or stopping on a dime can look really bad. Who's ever seen a game where like the NPC walks forward and then turns like really jittery? It's not very nice. So steering, what we're going to do is steering is going to apply a sort of force to smoothly guide entities toward a target. And in order to get full marks in assignment 2, we're going to be implementing some steering behavior. Excuse me. So what is a steering behavior? Okay. So let's say we're in a game and we're at a specific position. Okay. So we've got some entity in our game represented by this square. So say this is like a light particle or a Mario or Zelda or something like that. And we are currently moving along this trajectory. So we've got a velocity, and the velocity in our game is going to be the change in X and Y position of the NPC. So this entity currently has, and by entity I mean anything in the game, okay? This entity currently has this velocity. But let's say that at some point, that velocity we want to change. So we want to change from moving in a straight line to get to something, right? Maybe that's toward a goal location, it's toward the player, it's toward some bullet or health pack or whatever. So at some point, there is some target that we want to hit. And so this dashed red line is the desired direction that we want to go in. So for example, we're currently heading along the blue line. That's our current trajectory through the game. But we want to head toward this target. So if we didn't care about realistic or smooth movement, what we would do is instantaneously change our angle right here to be moving along this red line. But that's what we want to avoid, right? So with our current speed, so speed is the magnitude of velocity, remember. So if we get the length of this vector here, that'll give us our current speed. Our desired vector of travel is this red vector, okay? So that means that if we currently want to be heading in that direction at that speed, but we don't want to instantaneously change to make our movement look really, really bad. So here's how we would calculate the desired vector, okay? So if we have a target position and we have a current position, the way that we get this vector, I forgot to do the 2D math intro. Yay, okay, but that's fine. You know all about this. So this is very simple, like math 2050 vector add, addition, and subtraction. Very, very easy. So if you have the target position and you subtract the current position, what you get is this desired vector. Okay, well, you get the dashed vector here. So if we take target minus position, we get the dashed red line. But what we want is the desired red line. So what we do in order to change the length of this red vector, or the dashed red vector, into the length that we want, which is the length of the blue vector, is we first normalize this vector, convert it to length 1, okay? And then we take the desired vector, which is currently of length 1, and multiply it by the length of the velocity vector. So that is how we get from this velocity to desired velocity. Okay. So now we've got how do we get that desired velocity? And it's from subtracting the current position from the target position. But how do we implement steering? So here's what steering does. And if you did 4300, you've already been given this lecture before. But steering is going to be a force that turns us smoothly from my current velocity to the desired velocity, okay? So instead of going like this and then boom and like this, what we're going to do is turn like this gradually over time. So this green vector here, this is if we take the desired velocity and we subtract the current velocity, what we get is a steering vector, okay? So that steering vector is the difference between my current heading and the desired heading. So if I add this full steering vector to my current velocity, what I get is the desired velocity. So I don't want to go all the way from my current velocity to the desired velocity, however. So what I'm going to do is I'm going to scale the steering vector. And remember, scaling a vector is just multiplying it by some constant, right? So if I have some scaled version of this steering vector, we can consider that some force that's acting on our current vector, right? So if I'm currently heading in this direction and along comes the steering force, it's going to slowly push me in that direction. And that's what this green vector is it's telling us we want to add, like to go not all the way toward the desired vector, but a little bit toward the desired vector. So what we have is now this actual, the black vector here, which I'm calling actual, that's the actual velocity that we want to have on the next frame of the game. So if we take the current velocity and add this scaled steering force, what we get is the actual vector. So how do I calculate that actual vector? Is there anything different between these slides? No, they're not. Okay. How do I calculate the actual vector? Well, first of all, what I need is I want to scale my steering vector by something. So if the scale, so like this x value here, the scale value is going to be, all right, so if I have a value of 0 for the scale vector, then my vector will be of length 0. And if I add my current velocity to a steering vector with scale 0, I get the same thing. I don't add anything to it. However, if my scale is 1, then what I get is the entire steering vector. Okay, and I don't want that either because that's going all the way to the desired vector. So let me just erase these values. Okay, so how do I get this black vector, which is the one that I want? So first I have to choose a scale value between 0 and 1. Don't choose 1 and don't choose 0, right? So maybe we have this like 0.1 or something like that. So 0.1 would give us every frame of the game, we would be scaling ourselves 10% toward the way of the desired vector. Then the steering vector, as we said, is desired minus velocity. Then we take that steering vector and we scale it or multiply it by the scale that we wanted to have. And then the actual vector that we want to end up with is now velocity plus steering. Okay, so we take the blue vector, which is our current velocity, we add the steering vector, which is how much we want to turn, and then we get the actual velocity. And that is the steering. So let's do that in code, because sometimes it's a lot easier to look at things in code, or at least I find it's easier to look at in code sometimes. So let's move my camera down here a little bit. So let's say we're giving, well, here's the velocity, actual, and desired, and target, okay? So if we are given velocity, which is our current velocity, we're given the target, which is some point we want to go to, and we're given the scale of the steering force, here is how we compute our steering vector. So first, desired is equal to target minus position. We get the desired vector. Then we normalize the desired vector so that it has length 1. So desired is equal to desired divided by desired.length. Oh my, there we go. I'll move this up a little bit. Then what we do is desired, we have to scale it to match the length of the velocity. Okay. Oh yes, we're given position as well, obviously. Sorry. We always have our units position, but I didn't put it here for some reason. Apologies. So after we've normalized the desired vector, then we have to multiply it by the length of the velocity vector, and that gives us the final red desired vector. Then steering is going to be desired minus velocity. That gives us this whole dashed green line. Then we want to scale that steering vector by our steering factor, right? By our force, which is like 0.1 or whatever. And then we compute the actual vector by taking the velocity vector and adding the steering vector to it. Okay? So that's how we do steering. Very, very simple math. But I have told you so far, I've kind of misleaded you into telling you that all steering does is smooths motion. But that's not true. Steering can actually implement behaviors. So the behaviors of steering, the way we implement steering and the mathematics behind it can also implement behaviors. So what we have just described in computing this vector is actually called a seek behavior, okay? So a seeking behavior of steering, it computes a steering vector which makes us seek toward the target. So we are always chasing toward the target. Even if the target is moving, this will keep us chasing toward the target or seeking the target. However, sometimes that's not what we want, right? Let's say if we want to actually catch up with the target, maybe we don't want to always be chasing behind it. What we want to do is pursue it by moving to where we think it will be, right? So if we know the target's velocity, or we have some estimate of the target's velocity, well, we can do the same mathematics, but instead of using the target's position, we use target position plus target velocity to compute the place we want to go to. And if we do this, this is called the pursuing behavior. So what we calculated first is called a seeking behavior, and what we calculate here is called a pursue behavior. Now, you might say, okay, those are kind of the same thing. Give me something different. Why is there, show me something different that steering can do? Well, steering can be used, the exact same math, if all we do is if we flip the desired vector, so we multiplied the desired vector by -1, then we have a fleeing behavior, which is really cool. So if we see, if we're playing, who's played agar.io, that snake game where you had to avoid other snakes? If we see a huge, if we're a medium-sized snake, if we see a small snake, we want to steer towards it, right, to eat it. But if we see a big snake, we want to flee that and go away from it. So we can use the exact same math and just reverse the direction of the desired vector so that it's pointing away from the target. And then we have a fleeing behavior. Okay. Someone in the chat mentioned we might get orbital mechanics by accident. That's a very, very good point, and that was actually my next slide. So let me show you. Okay. So something else that we have to define with steering is called an arrival behavior. What is an arrival behavior? Well, it has to do with this sort of orbiting or oscillating that you can find with steering. So one issue with steering is that the closer we get to the target, is when we get really, really close, the entity can oscillate, okay? So it can go back and forth, back and forth, back and forth. And we must define an arrival behavior. And that means as we get closer and closer to the target, we want to change our behavior slightly in order to make things do what we kind of want them to do. So the simplest solution is that we can scale the speed linearly as it approaches the target within some distance, right? So just think about you're parking a car. Your arrival behavior, you're driving 60 down the road, and then you get to your parking spot, you're going to slow down as you back into the parking spot, right? You're not just going to, unless you're some crazy like Jason Bourne or something, you're not going to like spin around and perfectly get into the parking spot. So you're going to want your arrival behavior. So as you get closer and closer, you're going to slow down more and more. And there's no best value for this, right? It's completely dependent on your game. And so if you don't have, or Ace Ventura, like someone said, if you don't change your speed, then what you can get is a behavior like the following. So let's say, let me just erase this so I have a bit of a blank canvas. Let's say this right here is my target position. Okay, so this is my target. And let's say that every frame I'm moving by this amount, right? So I've moved from here to here to here. And now what I'm going to do is I'm going to overshoot my target because I'm not slowing down, right? And so if I overshoot on one frame, then the next frame I'm going to want to go back and I'm going to overshoot again, then I'm going to overshoot again, and I'm going to overshoot again. And so if you're lucky, you'll get an orbital behavior. But if you're not, then you're going to get this weird oscillating type of behavior. So you also want to have like a stopping behavior. If you're within a certain radius, you just stop or kill the enemy or whatever you do, right? So just make sure that when you implement steering that you have some sort of arrival behavior as well. Okay, so here are some examples that I found online which are really nice. So this is a really good example of a seeking behavior. So we're clicking a target on the screen and you can see that the cute little kitty cat is not just turning on a dime, right? You can see this smooth steering like the cat was a car, I guess, if the cat is driving a car. Now, of course, an actual cat can definitely turn faster than this, but I think it gives a kind of nice feel to the game where it's like a professional video game now because you're actually moving, you're staring around. Steering can also be used for avoidance, right? So instead of the fleeing behavior, we can have avoidance forces. So for example, if up here we have one target and here we have another target, we could say compute the distance between them and then head toward the middle of them and use steering to do that, right? So that's a really cool thing. There's all sorts of different behaviors that you can do with steering. We're close to the end of the lecture, and this course is not all about steering. But I just want to show you some examples here where you can also have like really complex group avoidance behaviors. And this gets into things like almost how animals behave, right? So if you've ever seen something like Boyd's simulations, which I think I will get into a bit later on in the course, this is how those sort of things work, where you're sort of following the person in front of you, but avoiding people to the sides of you, stuff like that. So you can combine steering behaviors as well to get these really interesting pathfinding or path following examples. Well, I'm not going to open this up right now, but if you're interested in more steering demos, there is a really cool steering demo on this OpenSteer, it's called. You can download the software, you can play with it, you can see all sorts of different steering behaviors and implement those in your games if you want. Okay, so that is it for today's lecture. I always like to end it by going back to the course schedule just to see where we are. So we just did movement in games, okay? So it's an introduction to movement. So the process of like identifying a problem, choosing a space representation, choosing your algorithm, then so doing the pathfinding, then choosing the method of path following, and then maybe applying some steering, okay? So that's the overall how we do movement in games, but of course we hand waves over all of those algorithms, and then later in the course we're going to be getting into some of those algorithms. So in the next class, we're going to be going over the grid space representation and how that's used in games, and all sorts of different ways that you can use grids in games to accomplish certain behaviors. And then in the next class, we're going to actually be going over some very specific algorithms like vector fields, influence maps, that sort of thing, that use grids as the underlying data structure. Then in assignment 2, we're going to be implementing what we learned here to do a grid-based navigation mesh and implement some influence map pathfinding and some steering behavior. Okay, so we're finally into the actual content of the course after the intro week lectures, sort of. So I hope you're having a good time. I really love this sort of thing, and I think we're going to have some fun going forward in the course. So thank you all for tuning in, and I will see you on Tuesday.